In section 14.3 we're talking about exponential modelling, and there are two main ideas to get into your head here. There's lots of situations in real life where exponential modelling is used, and there are two ways of thinking about it that I'd advise. One of them is to think about the price of something, and the typical example, and I think there's an example of this in the exercise, is the price of a car, all right? And the second one is, well, there are two actually. Exponential growth can be thought of as a population that's growing, so that, population of a country, and I think there are two examples at least in the exercise. And the other thing would be money in a bank account and compound interest, okay? So let's just have a think about those, and you'll be familiar with these ideas from GCSE questions as well, where it's maybe called exponential growth and decay, or compound interest and compound decay, or repeated proportional change, or something like that. It's the same kind of idea. So let's just have a think about it and how would it work. Well, let's take the example of a car. We buy a new car. Let's say it is worth £40,000. We're buying a brand new car for £40,000. Now, after a year, that car is going to have lost a percentage of its value. So keep the numbers easy. Let's say it loses a quarter of its value in the first year, okay? And cars do decay like this, right? The amount of money you lose if you buy a new car is substantial in the first year. And it's something, I don't know, I don't follow the markets of how much cars are worth exactly, but this is not a ridiculous number here, okay? In the second year, it's going to lose a quarter of its value again, okay? Well, if it loses a quarter of its value again, it's gone down from 40,000 to 30,000 here. But it's not going to go down another £10,000 because its value here is only £30,000. So it's going to go down by a quarter of 30,000, okay? Now, rather than keep doing the actual arithmetic, I'm just going to try and represent this. Now, in the third year, it's going to go down by a quarter, but it's going to go down by a quarter of this number. And then the fourth year, a quarter, but a quarter of this number. So I'm going to get this sort of shape to my graph, okay? I'm going to get this sort of decay curve. You see this if you're doing science in radioactive decay as well, works in this sort of way. So essentially I'm getting this shaped graph. Oh dear, I can't draw a neat one. So what's going to happen if I've got that repeated change, it decreasing by the same proportion each time, not the same amount, we're not taking away the same amount, we're timesing by the same fraction each time, then we're going to get that sort of decay, all right? And where have we seen that before? Well, if you remember that something to the minus x graph, it looked like this, didn't it? So this graph looks very much like this part of one of the graphs from section 14.1. Now, if we've got an exponential decay, we can think about, well, what would the constant be here, and try and model it. But what would really happen in everyday life, you might get some data, and you might be saying, all right, well, this data decays exponentially, and here are my data points. And then in the same way as you might fit a line of best fit to something, you might get these data points and think, well, there's a curve of best fit, and that curve of best fit sort of looks like this. Now, you could think of that and say, well, that is an a to the power of x curve, sorry, a to the power of minus x curve. Or you could think of that and say, well, it could be an e to the power of minus x curve times by an appropriate number in front to squash it up or stretch it out. Now, why would we use e to the power of x when we could change this number? Well, the reason for that is if we just know a lot about one of these exponential functions, 2 to the power of x, or 7 to the power of x, or 1 to the power of x, or not 1 to the power of x, 1.5 to the power of x, if we know a lot about one of these functions and then we do the transformation on it, we can use what we know about, if we made it 2 to the power of x every single time, then we could use what we know about 2 to the power of x maybe to answer questions about this, okay? Now, that's what we do, and the convention is that the useful number is the e to the power of x. Now, you might think, well, hang on a minute, if we get to pick a number, why have we picked e, which is 2.71828? Why would we pick that number? Why would we not pick an easy number? Well, the reason is, if we're doing this, we're looking at the change, aren't we? We're looking at the rate of change. We have a car which is worth this much, then it's worth this much, then it's worth this much. It's a changing sort of question. Something is changing over time. And if something is changing, you might want to be looking at the derivative. You might want to differentiate that function because the derivative tells you about the rate of change, how quickly something's changing. And in that case, let's pick the function which is easy to differentiate. So we pick E as our sort of standard base there. Now, all of that really is slightly by the by. You can answer all these questions without needing to know any of that, but that's the background. That's why that's why this is in here. That's why they're bothered putting it in the first year of A Level, because they've decided if we're going to show you anything about exponentials and logarithms in the first year, why don't we show you this model, because it is a model that comes up in a lot of places. Okay, so that's the first one, an exponential decay model. The second model would be something like a population growing or money in a bank account growing. So let's take that example. I put some money in a bank account. I've got this much money in a bank account. Let's make it a sort of silly amount of interest. Let's make it a 50% interest. All right. So after the first year, it goes up to 1.5 times what it was worth in the first place. After the second year, it goes to 1.5 times what it was worth. But that is 1.5 times this number here, this height here. So I'm going to increase it up to here, and then 1.5 times that, and 1.5 times that. So again, it's this exponential growth curve. That shape looks very like an a to the power of x graph, or rather than a to the power of x, it would look like e to the power of x with an appropriate constant in front to squash it up. Okay, so we pick our constant to squash it up to fit the curve of best fit, and there are clever ways of doing that which we're not going to go into in this chapter, and then we get our model. Okay, so we've got an exponential growth model, we've got an exponential decay model. Other than that, you've got to read the questions, look at what they're asking you, and really sort of use a bit of common sense and mathematical nous for solving the questions. The only other thing that might be useful for me to point out here, other than go and read the examples and see what they say, is if you've got something like this. So I've changed the x into a t. So this x-axis is often a time axis in these questions. Well, that shouldn't be too much of a problem. This y-axis is often labelled as something else. So in this case, I'm looking at example 5. This is a pesticide. The density of a pesticide in milligrams per metre squared. Well, I don't know anything about pesticides and milligrams per metre squared, but I know that P is kind of how much pesticide we've got. We've called it P instead of Y because P stands for pesticide. So this is the model we're going to use. From looking at this, I can see it is an exponential decay model. It's got an e to the minus x times e to the minus t times something in it. So I expect that the graph is going to be that shape, and I can draw that without having to think and draw it on my calculator or anything. I can just look at that and go, oh, it's one of those exponential decay ones, right? Second thing is, when t equals 0, this is e to the power of 0, which is 1. So 1 times 160. So when t equals 0, p is 160. So that number there, that coefficient term, is where it hits the p-axis, and that is how much pesticide there is when time equals 0. So that's kind of the starting amount, if you like. Now, if we just have a quick flick through the exercise, I'm going to ignore all the words. Let's just look at this. Look, when t equals 0, v equals 20,000. So the starting value of our v, when t equals 0, before we start the clock at the start of the question, v is 20,000. Here, when t equals 0, p equals 20 plus 10. So p equals 30, whatever this thing is, p has an initial value of 30. N here has an initial value of 300, take away 100. So initial value of 200, okay? So you can see the initial values from the question when you've got a bit of practice. Now again, you don't need to know that, you can work that out as you go. If you want to know the value of p after no days, then you put t equals 0 in there and that will give you p, but it helps to kind of be aware of that, and when you've done a few questions, you'll start spotting that sort of thing. That seems like quite a long video for a section where you probably could have just read it and started the question straight away, but there's a bit of background there which you might find useful or interesting in some sort of way. Okay, that's end of section 14C.